Okay, thank you for this introduction. Yes, I will talk to you actually a little bit about, if you like, personal history, because I kind of originated or was raised with formal language theory. So, and this is kind of back to that a little bit. Well, maybe many of you might think, just from their education, bachelor course or whatever, that finite automata are really the easy things and nothing really interesting about that. But as most of you think on graph problems, I mean, of course, automata are, in a sense, nothing else than specially color-directed graphs. So you can easily think of them in terms of harder problems. And the three classical problems I will mostly focus on during my talk are the following ones. So non-universality means you're given an automaton and with some input alphabet sigma, and you ask whether the language accepted by this automaton is just sigma star, so every word over this language. Or in equivalence, given two automata, A1, A2, we ask whether or not the two languages accepted by these automata are the same, or are not the same. And intersection non-emptiness, well, you are given a bunch of automata, and you ask if there is any word accepted by everybody. Yeah, so these are the three main problems I will focus on. Why? Well, if you think about it for a sec, you will notice immediately from what you've probably learned in bachelor times, that for DFAs, at least non-universality and inequivalence are p times, so quite easy. However, if I turn my attention to NFAs, all three problems sort of suddenly become p-space complete. And this is also true if I consider this intersection non-emptiness for DFAs. So this is just the kind of classical status. And maybe even more interesting to those interested in graphs is that if I go sort of towards NFAs now for a sec, due to these hardness and softness results I just presented, a case is the fact that all these problems are still hard, namely in this case NP-complete, on unary input alphabets. And okay, if you have unary input alphabets, what does it mean? Basically, you can simply forget about this structure as being an automaton. It's just a directed graph, nothing else. So you can also kind of think of like non-universality or universality in terms of graphs, if you like to have it like that. So maybe you are living here in this blue house and you want to visit somebody in this red house, and in between there is some directed graph which kind of describes the possibilities how to walk from the blue house to the red house. And somehow, say your doctor advised you to walk as long as possible, but still you want to stay in your schedule. So maybe you know walking each of these arcs takes 1 minute, and you have 35 minutes left, and you want to know whether now you can use up all the time to walk from here to here, for instance. So this is kind of the universality problem in disguise on direct graphs here. So I must underline it's important to be directed here. For undirected graphs, this whole problem becomes easy. Anyways, as I mentioned, these problems are hard for unary alphabets, or in more complexity theoretic terms, for tele-NFAs. And this hardness was already shown by Stockmeyer and Meyer long ago. Why I'm mentioning this here, and I'm also putting up this nasty slide, a pretty technical slide, because what I want to do in the following is trying to get some lower bound results, and so under ETH. And therefore, it's, for instance, interesting that Stockmeyer and Meyer's proof actually reduced from 3 set. And so in order to understand what kind of lower bounds we can immediately grab from their reduction and what are the weaknesses, where do we have to improve on that to get better lower bounds, we have to understand what's going on here. So basically, how can we actually codify anything within unary languages? The basic trick is to use Chinese reminder theorem. And similar actually, last talk there was something like that, at least in passing. So for instance, you just, if you take the first n primes, if you have an 3-set instance on 3 variables and m clauses, like in an example, P1, 2, P2, 3, P3, 5. And now such a unary word like a to the z that encodes an assignment alpha, well, if and only if the z is the same as the assignment to xi modulo pi. Okay, for instance, if your assignment alpha says, well, x1 is 0, so false, x2 is true, x3 is true, then the number is something like 16. At least if these are all the variables that appear. Otherwise, you have to basically do more of that. You have a larger number, say. Given that, what do you have to express in order to encode satisfiability? Well, first of all, I try to write down what it means to be some word which is not encoding any assignment. Okay, that means that basically we falsify this condition here. So we have, for instance, a j equals 2 less than p to the kth prime, such that this it is a word of this form. Yeah, and so this is one thing we have to check. So that all the assignments that kind of survive, all the words that kind of survive actually codifying assignments. And then second thing is that I want to express that an assignment falsifies a clause. So LJ is kind of giving me somehow this statement that a certain assignment, in this case this z sub kj, is actually falsified. So which means that, okay, what does it mean? If I want to falsify a clause, there's exactly one way to do this. And this assignment is actually codified in this kind of thing. So the next thing you have to see that the automata that kind of can be used to express these languages are very simple. So they're basically cycles of a certain length. Somehow these multiple of these p k's, and taking all this together, it's not so hard to see that, well, you gotta prove, or if you take any number, so either it does not codify an assignment, or it does, and if it does, then, well, if it's really in the language, then it falsifies some clause. So therefore, we have this kind of reduction. And how many states does an NFA have that basically takes all these together? So you might recall that union is an easy operation on NFAs. So basically we have to look at the question, how many states do automata need to process this and this? And just because we have 3 set instances, we know that this is basically, something like Pn cube states at most. And now, again, something similar to the previous talks. Well, this is somehow like n log n in brackets square cubed. And how many of these languages do we have? M. So we have something like this. So all in all, we would get immediately from this old reduction such a lower bound. So how can we improve to this? Or is it possible at all to improve on this somehow? So how can we actually show this? What are the algorithms available to show universality? And so the textbook algorithm, we all know, would basically convert this NFA you give to a DFA, and you would have something like this complexity as for your algorithm in the worst case. But there is some improvement. And namely, this special case of unary input alphabets, there's some well, it's known that the worst case size of DFAs is slightly less than this, namely this. It's a kind of funny formula, so we are getting now into this descriptional complexity issues of formal languages. But anyway, so this is what you can get. So there's still some difference, as you can see. And so next I wanted to show you is a bit how to improve on these lower bounds. So one thing you might have seen with this idea to express that a certain clause is falsified. Well, we need these 3 primes to be multiplied. Well, maybe you can do better if you don't go for clauses, but instead say for edges of a graph. So what does it mean not to satisfy an edge? Maybe you more or less get to the idea of coloring. It's not that far away. And so also this morning we have seen that we have also this O star 2 to the little o of m number of edges, lower bound for 3 colorability. Therefore, we can basically mimic the reduction of Stockmeyer and Meyer and adapt it to this situation, modulo details, say, and what we get is then, instead of this 1 over 4, a 1 over 3, but there's still this epsilon hanging around. Where does it come from? It comes from these polylogarithmic terms, which are kind of inherited by this encoding with the first n prime numbers. But we had some little waste. The waste was to throw away many of the possible encoding numbers due to the restriction that we are only interested in those which are 0 or 1 modulo something. So we have some space left, and we can actually use this by a more clever encoding. And well, with some tricks, as I mentioned, you get away losing this minus epsilon thingy. So this is what we finally get at the moment. But of course, there's still a gap. So I don't know how to fill it. But anyways, this is how it is at the moment. For the inequivalence problem for NFAs, we basically get the same kind of results at the moment, at least. So still, this kind of lower bound and this kind of upper bound. So you might think that this is a bit of a harder problem, and it might be actually that it's easier to improve here on some kind of bounds, but I don't know. So at the moment, this is open. Kind of even worse, if we look at this intersection problem, then, so we are given a bunch of NFAs, and I try to see whether or not the intersection of all these languages is empty, around empty. Then we can get some really weird function here as a lower bound, where this little k is the number of automata we are dealing with. Well, it is basically looking at the previous constructions, and as I tried to indicate already, if you look back at the NFAs or also DFAs that are accepting this type of languages or also these type of languages, they have a very special and easy structure. So therefore, it's not hard to see that they can be used as cornerstones to look into the complement. And complementation, at least for NFAs and complementation for these languages, yeah? And then you look for the non-emptiness instead of the universality or non-universality on the other hand. So this is basically the gist of this kind of construction. And looking back also in the figures, so now for the coloring stuff, we get this kind of scenery, and that basically gives these kind of funny figures up there. But unfortunately, really unfortunately, up to now, the only thing I know to really solve this algorithmically is doing some kind of product automaton construction. And this gives me an automaton which has this many states, basically. And so this is at least my current bound, and, well, I must admit this is pretty far off. This situation can be a little bit improved if I now abandon this very specific unary alphabet thingy. So if I now go into the case of bounded alphabets, first of all, say binary alphabets, then I can also show that doing some different but still related reduction from 3 coloring, we can rule out algorithms with a running time of O to the little of q in the number of states of the automaton for the non-universality problem, and which is actually now matching this DFA construction I mentioned before. So in that case, we are fine. Well, basically the same we get also if we get, so this was for, for inequivalence. Same kind of a construction, same idea. So that is fine. So for that case, we match lower and upper bounds. And also, even with a kind of trivial algorithm like the subset construction, yeah? So it's nothing cute in the sense, nothing very weird, but still it works. If we look at intersection non-emptiness for DFAs, so then we again get some things which are just derived by the previous constructions, which are not really tied, so to speak. For the case of unbounded alphabets, okay, now we are moving further on. So now the alphabet is actually a part of alphabet size is a part of the input. Then again, we get some kind of matching bounds, basically, so ruling out, given the intersection problem for DFAs, so KDFAs, each with at most 3 states, which is not too much. So we get this kind of lower bound, and so of course the product automaton construction gives you this kind of upper bound. So this is kind of pretty tight, and at least under ATH. So maybe to give you an idea how this construction works, because it's pretty simple. So for the vertices and for the edges, we have some kind of automata. So, and what do they do? Well, this automaton basically tells you that, okay, and what's the alphabet? That's crucial here. What's the alphabet? The alphabet is this kind of product thingy. So, which means I can have pairs of vertices and colors, which is quite a lot of information in the alphabet. And so these AV automata, they basically ensure, so here we start, here we end, that there's exactly one color associated to each vertex. That is spelled out there. And then this kind of automata tell you that there is some A, at least because we intersect all these, there is some color A such that both ends of this edge are colored with the same color. This is basically telling you this. And therefore, well, intersecting all this gives you the reduction, basically. Yeah? Okay, so just to sum up this part, and I will be quick with the other one. We have, well, basically one line with unbound alphabets where we are kind of happy, especially if you fix Q somehow, then this is really all tight. Fine. For the other cases, we have sometimes really strange situations. So I'm just talking about this function in the exponent, which looks a bit weird, but otherwise it would be too small. So we have always these kind of things, for instance, which are kind of weird, and this is even worse in a sense, if you look for lower and upper bounds. But this is how it is at the moment for us. Maybe you have ideas how to improve these things, so please tell me. I wanted to sketch at least, in the following couple of minutes, some more problems. So you see we are just up here, but I will be speeding up now. So there are really a couple of more problems on finite automata, which are hard. For instance, a periodicity. Well, I will be short with this slide, but this is one of the most interesting sub-regular language classes. They can be described, for instance, by in many ways. So there are many characterizations. One of them is to say, well, we try to build up regular expressions, but not with Kleene star, but so starting from finite steps, Boolean operations and concatenation, nothing else. So Boolean operations include complementation. So therefore you can get infinite sets. But it's still, you don't have Kleene star. And these have many ways to see this, for instance, algebraically with solvable groups of the syntactic monoid stuffy. I won't go into these details, but just to mention, we can basically mimic an old use an old reduction of Jacques Stern that is kind of not so interesting anymore for the classical world, because Jacques Stern only showed that trying to see whether a given finite automaton accepts an aperiodic language is co and p hard. And it is known to be a p-space complete, this problem. In a sense, this reduction is not more interesting, but it's interesting for us, because it gives you this lower bound if you analyze it, reanalyze it under ETH conditions, while currently this is what we know for really showing or testing a periodicity for a given DFA, Gusted DFA. So there is still some gap, but Andreas at least is hoping that he can improve on that green stuff here a bit, using some algebraic tools, basically. Another thing you might have heard of, synchronizing words. That is related to one of the most famous open combinatorial conjectures in formal language theory, the Czerny conjecture. I won't go into details here again, but just mention one more kind of add-on to what we've done before. Namely, if we look at the problem to synchronize a given set of states, in the sense that we want to require that there is a word W that if I start my automaton in Q or in Q prime, it doesn't matter, for any QQ prime in my Q sync set, it will give me this lead into the same state. That's some funny write-up for that. This can be solved in O star of 2 to the Q, basically also by a subset construction, while you can show a matching lower bound for that. Or we can show, yes. At least for bounded alphabets, binary alphabets, for instance, as well. Okay, let me jump to 5 minutes. Yes, jumping finite automata are a concept which kind of uses finite automata in a different way. Namely, it allows to read portions of the input here and there, say. For instance, if I have this finite automaton and I try to start it now, it can read this, it can jump here in the input or here, doesn't matter. I read this part and then I read some other part. So these are just two ways to read the same input word, and I go around, until I'm finished, of course. So what I get is, in this case, all words that have the same numbers of A's, B's, and C's, which is a non-regular language, a non-context-free language, as we all know. So for these JFAs, there's even hardness, for instance, for uniform membership. So there are actually different proofs. Here's, by the way, the same Stockmeyer, but a different Meyer. So they had a proof for that in some other models, but which are equivalent. And we have another one, Wojciech-Worrell sent us another one, and actually that is the one which we use for the ETH thingy, to basically have, again, some, lower bound like this for the universal membership, while the upper bound we currently know is this one, so it's not exactly matching, but still some work to do. This Bostrophinon finite automata is another way of using finite automata for reading pictures, two-dimensional objects. So basically this little guy here, what does it do? It will read through the picture like, a cow ploughs. So this is this kind of Bostrophinon thingy, so going all the way around, and it will only detect these borders. And for this kind of way of working on these two-dimensional arrays or pictures, we can show that, for instance, non-emptiness is NP-complete, and some other stuffy. And if I look at this from the ETH perspective, I can see that, for instance, I get something like 2 to the little of square root of q lower bound, while for the emptiness problem, while I have the q to the q algorithm, I don't know better at the moment, for testing emptiness, non-emptiness for these type of automata. Okay, let me conclude. Although you might think that finite automata are not that interesting anymore, there are still some quite interesting hard problems for these. And I think, apart from our paper on synchronizing words, frankly speaking, I don't think there is anything there's ever done on this before. So there are still many open, concrete questions to match these lower and upper bounds, currently at least. For instance, these funny, I don't know how to get anything like that in the reaction. No idea, I must frankly say. So, and things like that. Maybe there are other ways to do this, apart from DFA construction. And just one last thought on this. Currently, as tradition goes with finite automata theory as well, we are measuring complexity always in the number of states. Well, number of nodes of a graph, if you want to. But of course, you can look at it from the position of the number of transitions. Haven't done this so far, but maybe this gives you new ideas, at least, to match lower and upper bounds. Okay, thank you for your attention, and thanks for people who helped me come here.
Time for questions? So the reason that the strong ETH doesn't appear is just that you haven't got around to it? There was a concrete bound like the 3 to the k for the product construction?
Okay, sorry. I didn't look at it for that case, but actually there are... okay, I just plugged it in. Sorry. There are... Just a sec. For instance, for this problem, you can also ask... or for this type of problems, or have additional parameter like the number of, the length of the word you want to have as a testimony for this, for this property, on this W. And if you parameterize by that, then you get some lower bounds on SETH. And I think similar construction also work for other problems. So if you, you always have this idea of having a testimony. You need some witness to show you, okay, you're non-universal, stuff like that. And if you bound that, so that's also known as the K-bounded or L-bounded problem in literature, then I think that would lead to some SETH-based based results, but I didn't check that for the other cases. It's just my gut feeling.
Okay, anything else? Otherwise, let's switch to search and thank the speaker again.